story. So we're going to see a relationship of what we did in the previous section and in the story of series of adding infinitely many terms together. So how can I possibly produce a relationship with functions or with actually sequences that they discussed before? And there is a way to do this. There is a way to produce so-called partial sums. So if you take just a part of your series, the first term, and then the sum of first two terms, and then the sum of first three terms, and so forth, all the way to the sum of n terms. And that's how they produce pieces that compose a sequence. And the sequences is what we discussed in the previous section. And what we were doing is we would take the limit of that sequence. Because what we cared about was the limit if it exists or if it does not exist, and the limit of sequence of partial sums. That's the term that deserves some thinking. So what this is, and that's actually what they are. And of course, it can continue infinitely. So you add new term to the previous n, so that'd be s n plus 1, and then n plus 2, and that's where this limit of, again, those partial sums is coming from. And the point of story, this limit, if it exists, we call it the sum of the sequence, which is usually called with letter S. So infinitely many terms added could be treated as if you take the limit of the partial sums sequence, and that's S, and that's what we can find, and that's where it ends up being. So they actually start discussing it here down below, so they call it as a capital S, the sum of this infinite series. And of course, this is very abstract, and the particular examples that we already observed last time with a so-called geometric series where we add powers of 2. So if you look at the example 1, part A, where you have 1/2 to the power of n, or 1 on the top and 2 to the power of n on the bottom, which is the same thing, and we produce the sum. And if we look at the partial sums, so if you add a part of this first two, you get 3/4, and then you add more terms, you get 7/8, and so forth. And eventually they saw that once they start to add these pieces, you end up with 2 to the n, and on the top is 2 to the n minus 1. Say, how do you know that? Well, we did it last time. Last time I tried to justify this idea, and when you take the limit of this partial sum, so now we're trying to see what is the actual sum of the sequence of partial sums, then this limit is going to be, well, looks like 2 to the power of n appears on the top and the bottom. So if you divide by 2 to the power of n numerator, as well as your denominator, so if I take my fraction and divide by the same exact number, algebraic expression, then nothing's going to happen, right, to the fraction. Algebraically, it's still the same fraction because I'm multiplying by that 1 over 2 to the power of n the top. And this way, things will cancel. So I'm going to end up with 1 here and 1 on the bottom. And my piece that I have remaining when n approaches to infinity will turn into 0. So we'll end up with a 1 for the limit. So that's what they do. Please notice they skip steps, and that's standard for calculus textbooks when they give explanations. So they expect you to fill the gaps. So anyway, the sum of this series is 1. And turns out it's very powerful to be able to see what the sum is, because usually we say the sequence of partial sums converges, and that's good enough for us to conclude what the sum is. But when we are able to actually find that limit, well, then we're actually giving them clear answer what this converges to. So turns out not too often you can find the limit. I say, really? Yeah, we'll see that, which could be surprising. But anyways, they have variety of interesting examples, but the big story is a geometric series. That type of a series where we can actually find that limit of what we just discussed, the sequence of partial sums. So it turns out when we have the previous example with 1/2 to the power of n, this goes under the story of theorem 9.6 that says if your ratio r, so it turns out that if you look back again at 1 over 2 to the power of n from 1 to infinity, then ratio is going to be 1/2. How come it is 1/2? Well, because when you take the first term, it's going to be 1 over 2 when n is equal to 1. And the next term is going to be 1 over 2 squared. Please notice that to move from first term to the next term, I need to multiply it by the 1/2. So that's how my denominator gets squared. And if I multiply by another 1/2 again, it'll be 1/2 cubed for the next term. So my denominator now is going to be raised to the power of 3, and etc. So it looks like this is so-called geometric series. And if I work with geometric series, turns out there is a formula for the sum. So this whole sum could be found using the result. So once you identified your ratio R, you also need to see what your first term is, where you starting with, and you're starting with 1/2, right? That's the first term. They call it as A, or A index 1, or A. And notice that A I multiply by 1/2 and again and again. So the formula is here. It is A, which is 1/2, which is divided by 1 minus ratio R, which is 1/2. And notice this has to be equal to 1, and it is indeed equal to 1 because you end up dividing 1/2 by 1 minus 1/2, which is also 1/2, and you divide in the same numerator by the same denominator, it is 1. So whenever your ratio is less than 1, Let me say, why is it 0? Absolute value is always greater than 0. Well, they try not to have it as a r equal to 0. So they could have just said r is not equal to 0, because then you start with 0 and the sequence will be all designed from zeros, and that's not, well, it's still going to be the same answer, but right, so it's like what, a over 1, so they don't want to have a 0 for ratio, because that'd be just a for the sum. So it's not really a sequence. That's why they say that r is strictly greater, which seemed to be obvious, but they just want to exclude the case when r is equal to 0. So anyways, when r is in between 0 and 1 in absolute value, or in general could be negative but small, between -1 and +1, then we can use the formula and calculate. And this is great, and this is quite amazing, and I can actually show you how they produce this little proof. I think it's pretty standard. So first term is a, the second term is a add a times r, and so forth. The nth term will be a sum of n terms, a and then a r and then etc. Please notice this last piece will be power of n minus 1, because there are a total of n many of them, right? Because we have the first term without power of r, like r to the 0 or whatever. So first is here, second, etc., up to n minus 1, and nth term is just a itself. And then I can do the following. I can multiply both sides of this equation by another r. So if I take and multiply it by another r, of course, n minus 1 refers not to the whole parentheses. I should be careful. It has to be multiplied only by my last term, right? So the parentheses actually close in here. So then I end up with r times a plus dot 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 and r to the power of n times a. And you say, Alex, why did you commute them? I don't know, it makes no difference really. But what does make difference is I notice that I can subtract the terms. So this is my r times Sn. So if I subtract from r times Sn, n's partial sum, r times just Sn. Why am I doing it? Well, because my goal is to know what the sum is. And the sum of the series is defined already, we saw it, is a limit of partial sums when n approaches to infinity. So that's the sum that I'm looking for. That's what I need to find. So when I factor that Sn out, I'm going to go r minus 1. And here, if I actually do the subtraction without r, Sn minus, actually Rsn times Sn, I notice that if I subtract from RA, they cancel, and so forth. They will all cancel, and the only thing that will remain is minus r to the power of n times a. So that's actually not minus, it'd be plus and the minus will be A, right? Because I subtract from the second row, first row. And then I can factor out A and have R to the power of N minus 1. So this is, on one hand, equal to that expression. On the other hand, it's equal to that expression. So how do I find Sn? So that expression or that expression. Well, looks like Sn, the partial sum, is going to be, if I divide my A times R to the power of N minus 1 by 1 minus R. You see, Alex, looks like in your case it's R minus 1 and it's 1 minus R. Well, if you multiply by -1 top and the bottom, that's the same thing. So you can always commute the negatives. And then you found the Sn, so doing this procedure of subtraction. And now you take the limit. Now you want to take the limit of this expression and notice that this term goes to 0 when it's less than 1. If you multiply number less than 1 by itself, so it gets smaller and smaller and smaller and smaller because it's less than 1. So you take a fraction less than 1 of something, so it makes it less. And that way, this disappears and you end up with only A and 1 minus R in the denominator. So this is your answer. And this is your sum, and that's what we try to justify. So this is worth to maybe get a piece of paper, pen and pencil, and to try to reproduce, because this is one of those classical proofs. And the key place to watch out is that your ratio needs to be less than 1. Then you add terms and you produce a meaningful sum. I think it's a good idea now to look at some exercises with this geometric series. So it turns out geometric series are good because they have a formula for the sum. Let's say if I try something like exercise number, let me try one with, see, these are all divergent. I need to get convergent. Less than 1, like exercise here, 25. Notice that the first term of this series is going to be when n is equal to 0. Please notice, by the way, that in some instances n is equal to 0, but in some instances n is equal to 1. First term is 1. So you want to make sure that you realize is that first term, which is dealing with A1 or with A0. And the result is different because of that. So when n is equal to 0, then my first term will be 5 over 6 to the power of 0. Right? This is 6, which is 1. This series starts with 1. What's the ratio? Well, it looks like it's 5 over 6 because next term will be 5 over 6, next will be 5 over 6 squared. And then I can use the formula for geometric series that we just produced that says it's A over 1 minus R. So it's straightforward. A is 1 divided by 1 minus R, which is 5 over 6. So I just plugged into this formula that we justified. A, first term, 1 and 5 over 6, and we end up with the answer. 1 minus 5 over 6 is 1, 6. And when we divide by 1, 6, we multiply by its reciprocal by 6 over 1, so the answer is 6. So we don't just say if it's convergent or divergent, we find the sum of it. Let me try 21. Looks like the ratio here is a little different. It's negative. And we don't care. We have a formula. We now can do all of them and doesn't really matter to us which exercise it is. Let me just scroll this down so you better see. So again, for exercise 21, looks like it's the same story. We have a first term that we care about and the ratio. And once we identify those, the formula is what's going to be used. So for the first term, when n is 0, whatever the ratio is, which is actually 1/4 with a negative sign. We don't care because we raise it to the power of 0, so it becomes 1. So all remains is 15/4. Okay, so we now can find the sum of this geometric series. The key part again, this is a geometric series. So we can use this formula. I say, Alex, why this is geometric series? Well, because if we look at the terms of this series, you will see that you actually keep on multiplying by negative 1/4. So signs will alternate, one positive, one negative, one positive, one negative, but the formula does not care for this. As long as your ratio in absolute value less than 1, absolute value of this ratio is less than 1, 1/4, right? Absolute value is positive 1/4, less than 1. Then we can use the formula. So looks like in my denominator, I'm going to get how many fourths? We add, right? 2 minuses, we have plus. So with 1, with 4/4, I add 1/4. 4 and 1 is going to be 5/4. And then when I divide these guys, so the 4 and 4 cancel if we multiply by 4 on the top and the bottom, the arithmetic, and then 15/5 is. Okay, so just like that. So nice little exercises. I think they're pretty straightforward. So anyways, whenever you have geometric series, as long as ratio is less than 1, we're good. Let me clean the mess. We'll move on to the next part of the story, which is the same section, but for not geometric series, for general cases, because geometric series are just too nice. And usually we cannot find the sum. We can only say if it exists, whatever it is, we don't know or not. So they say here in the theorem that if A, then B. So logical structure, you probably encountered that before. From A follows B. So if converges, then the terms are approaching to 0. That's important to realize because if terms do not approach to 0, and that's actually so-called contrapositive statement, not B, then not A. So it turns out logically they're equivalent. So what do you put bar? Well, that's not B. From not B follows not A. So it turns out that this is contrapositive argument, which is the same to direct argument. From B follows A, then from not B follows not A. And that's how most proofs are being done using the logical structure. That's something that deserves thinking about. But example, I guess you just take the examples, then it starts to be a little bit more clear. So if you say, okay, so from A follows B, what if B does not work? What if the limit is not there? Well, then A is not correct, because if A was correct, it would be B, but we don't have a B, you see? The idea, it's worth to also think about, because whenever we do proofs from contrapositive argument, it all goes into the structure that I try to put here as a little picture. So this is contrapositive statement, and that's what we use for testing diversions. So looking at the series, for example, 1 plus 1 plus 1 plus 1, dot, dot, dot. And notice that AN's term is 1. So you keep adding ones. It is less than 0. Let's write 0. Is this less than 1? Sorry. Less than 1. We need to make sure that our terms not just less than 1, but also approach to 0, right? So is this approaching to 0? N's term. No, it is approaching to 1 because it's 1, right? So it is not approaching to 0. So we can say that series is divergent. In fact, one can say the sum is probably equal to infinity or something, because it looks like you just keep on increasing and increasing and increasing and increasing by 1, right? And that could go infinitely high. Just take enough terms and whatever possible large number you think of, billion, take billion 1 terms and it's going to be exceeded. So that's how they say it's conversion to infinity. So infinite sum, and in general, this says divergent. See, but it converges to infinity. Well, we call it as divergent. That's important to realize. So if sum is infinite, then it's divergent series. So anyways, this is so-called test for divergence, and I'm gonna do another exercise and use this little test. Like I just saw here a bunch of problems 9 through 18 that all divergent. So why are they divergent? Well, look at the nth term. Nth term is 7, 6, which is raised to the power of n. Is it approaching to 0? No, it is greater than 1. It has to approach to 0. The point of story, it needs to approach to 0. If it doesn't, because our nth term does not approach to 0, well done, series is divergent. So notice that in all of these exercises, your nth term is produced by multiplying it by number more than 1. So it's increasing, it's getting bigger, 1 and little something. So it's some same thing and little extra. So it gets bigger. It's not getting smaller, so it's getting bigger. And well, for all of these exercises, using this little statement, they will diverge. The series will diverge. Numerators are bigger than denominators. Notice this one is multiplied by 1 and little something. And we don't care if it's negative or positive, as long as it is not approaching to 0, divergent. I say, what about that one, 14? Well, look at the nth term. It's going to be a fraction with numerator was n and denominator is 2n. So it looks like when I take a limit of it, it will approach to 1/2, right? It's 1n over 2, so it's 1 over 2. It is not 0. So it is divergent. So here is the square root of n squared, which is n, and n, so 1 over 1 is 1. So divergent. So all of these exercises, 1 or 1/2, looks like divergence. Let's say, well, what about this one? Well, that one goes to infinity. I think last time we discussed factorial is dominating function, so it's much bigger always when any power of n for any number, for 1,000 to the n, million to the n, eventually factorial will dominate. So it's going to infinity. It's not going to 0. So for your convenience, they put those divergent series separately to clarify they all divergent. So use that statement and you'll be fine. But later they mix exercises. So they put convergent together with divergent ones to have you, well, not to get confused, but to think which one you can use. So let me continue with divergent ones. Looks like 59 through 76 is what I'm talking about right now. So I need to get some room here to clean this mess. So right away I can see like 75 arctangent. See, Alex, looks like whenever you see arctangent, you're always trying to do it. Yeah, not favorite, but I guess that looks different. And again, looks like the arctangent, it just goes to infinity if you're talking about arctangent of n. Right? My favorite graph over arctangent. Remember how it looks like. Arctangent. Let's see. When you send your n to infinity, arctangent will be bounded. Sorry, it's not infinity, but pi over 2. So let me get a pi over 2. Plus pi over 2. And this is minus pi over 2. But it is not approaching to 0. Arctangent is here. It keeps approaching to pi over 2. When, see, it's always important to say when. So limit of arctangent is pi over 2. When x goes to infinity. See, how do you know that? From the graph. Right? If you keep going along the horizontal asymptote, you will approach to pi over 2. So it is not 0. The whole point of story, it needs to be 0 so the function is convergent. Otherwise, it's divergent. Just like that. So all of these fractional things are going to be divergent, but exercise number 69 is going to be what? I just erased it in that corner. It's geometric, right? You multiply by 1/2, 1/2, 1/2, 1/2. So that's a geometric series. Geometric. Let's see what you write. Yeah, I better write it a little bit more carefully. So whenever I say word geometric series, it means we keep multiplying to produce. So when ratio is 1/2, right? So just multiply by 1/2, 1/2. And ratio is less than 1. We just had that theorem. So it is less than 1. I see, Alex, in your writing, it looks like 4. Yeah, better write less than 1 carefully. And since ratio is smaller than 1, then it is convergent. In fact, you can find the sum of it. You remember the formula we used? The sum. So very good with that one. So whenever your denominator starts to dominate, you have suspicion for conversions, like 66 is 1 over n squared. It's convergent, goes to 0, and so forth with, well, what is so forth? Well, like 61 is this approaching to 0, no, to 1/10. Nth term is 1/10. Is it approaching to 0? No. Whenever it does not approach to 0, divergent. Same here. Nth term does not approach to 0. It's, well, probably approaches to infinity. It is, again, geometric series, and ratio is 1 point something, 0.75. More than 1, again, does not approach to 0, then divergent. It looks like they all pretty much, all of them are divergent, but a few convergent ones. But anyways, it's interesting to think about them, to look at them, and to try to do these little exercises. I was thinking about moving to the next section, but I don't think I want to do that. It may be a little bit too much. Maybe I'll just do another exercise from previous group of problems, maybe to take a look at exercise like 83, because that's something that we will discuss later in the chapter for so-called radius of conversions. What does that mean? Well, notice they have not one series in here. Like in exercise 83, they have infinitely many series. Problem number 83, they discuss various values of x. And notice that on the x-axis, there are infinitely many numbers, right? Such as 1, 2, 3. So what if x is 0? Well, when x is 0, it's going to be just sum of zeros. So that's the degenerate case. So that's going to be 0. So that one will be conversion. But what if x is equal to 1? When x is equal to 1, it will look like a sum of 1 to the power of n, which is just 1, or to the power of n. Oh, that's my favorite geometric series. It is convergent, and we can even find the sum. It looks like it is going to be geometric series in lots of cases. So if I take instead of x 2, let's say I'm going to take lots of them. Well, I'll show you that something different is going to happen when x is 2, because you have 2 to the power of n over 2 to the power of n. And this is sum of ones. When you say, Alex, when you take sum, you always say what happens with n. Well, it doesn't really matter. We start at n equal to 1 and go to infinity. So you have 1, 2, 3, 4, 5. Infinite. So it's divergent. So please notice that for these cases, 0, 1, there were convergent values of x, but when x is 2, or if you try x bigger, like 3, 4, 5, it's going to be always divergent, because it starts to be bigger than 1, so your numerator is bigger than denominator. So you keep adding numbers bigger than 1. And I say, oh, so then since this is geometric series, I need to make sure that I have my denominator that bigger than numerator. 1 is numerator, and well, probably, but that's for x equal to 1. What about if x is equal to 1/2? So you can consider lots of cases. If x is 1/2, and you can try to see that this looks like conversion. So whenever x is between 0 and 1, it'll be geometric series, and otherwise it's not. But again, the assumption we're going to see in more detail in the later sections. I just try to do this exercise just to take a little look at it, because I think it's advanced exercise. It's not for this section. It really has to be later when we learn the method to find so-called radius of conversions. But the major point why I looked at it is to make you realize that it's not really one single series here, because n goes 1, 2, 3, 4, but x is any real number. So you actually have infinitely, uncountably many series in this exercise, as well as in all of those where they have x. And that's more advanced, of course. So this group of problems I would probably skip. I just noticed that I decided to do it because it's really not that simple. It's more advanced. So anyways, let me do one more and we'll be done. So let me try one of these, like 45, 46, 47. Let me do 47, for example. 47 is sign alternating. So what happens when you start to alternate your signs? Well, it's usually easier for conversions, because if you have only positives or only negative terms, then you pile up more and more and more on the top, and you need to be careful to see if it's going to be infinite or not, right? Like here with sum of series that was designed out of ones, it's definitely pile up more and more and more. So it's hard to make it be conversion. Usually it is diversion, unless, well, things that we need to consider. But what if it's sign alternating, like in exercise 47? Well, again, what do they want? First question is always the same. Do they want to find this sum, or what are they asking for? They say find the sum of conversion series. So that's already a big help, because you already know that they discuss in conversion series here, right? Conversion. So I can recall the only way that we have to find sums, if you have the geometric series. Well, there are other ways, but usually they're not as straightforward. So for exercise 47, I can identify my first term, which is 3, clearly. That's where it starts. And then looks like the ratio is going to be 1/3, right? In fact, it's going to be negative 1/3, because signs alternate, so ratio is going to be negative, because when you look at the series of, that's what I don't need to write, but I'll still write it. So 3 for the first term, and then negative 1/3 is what we're multiplying it by. But the question is, what's the power? Well, if you put power of n, then for the n equal to 1, my a1 will be this is a1. A1 will be, well, just put 1 instead of n and see what comes out, right? Where? Well, here. So it'd be 3 times negative 1/3 to the power of 1, which is still negative. So it'd be 3 times negative 1/3, which is negative. Do I have negative 1 in here for my term? Yes. But this is not A1, it is A2. So for that matter, we start with a 0 and go to infinity. So our n then we'll start at 0. So if I try to look at first term, which is a index 0, then it will be my 3 multiplied by negative 1/3 raised to the power of 0. You see. And that's how I lose that structure. Negative 1/3 to the power of 0 is 1. So this is going to be just a number 3. So besides producing the formula for the nth term, we need to also make sure we start correctly. So our first term will be 3, not negative 1. So we're going to lose the first term. But anyways, our first term A is 3, ratio is 1/3. So I can even tell what the sum is. And if they ask me only for convergence, well, it is convergent because it's geometric. And if they want a sum, well, I'll use the formula. So my numerator is going to be A, which is 3, and my denominator is 1 minus negative 1/3. And then you do arithmetic. You add 1/3 and 1 is 4/3. So you divide 3 by 4/3. It's going to be 1 over. I say, really? Well, do arithmetic, double check. I say, that's amazing. The sum of this infinite series, which alternates, is only 1/4. Yes, isn't that amazing? We have a formula. So I want to add one last thing before you go, is that this is not what they asked me. I just did it for fun. Please notice all I care about first term and the ratio and produce the result. But just to make you visualize how we produce the actual series, because eventually we will be really heavily caring what first term is, because sometimes it starts at 0, sometimes it has to start at 1, sometimes it might even start at 2. And we can always vary this by changing the power of n, or n plus 1, or n minus 1, or n plus 2, or 2n if they're even powers. So these things are very heavily done in differential equations class when you start to work on that. So if you plan to take that class, well, pay attention to the series representation, especially to starting point. That'd be a good practice. So anyways, I think it's a good moment for me to stop, to let you enjoy the weekend, right? Another Thursday. So have a great weekend, and thank you for your patiently listening to all that. So I hope you will redo a couple of problems, like exercise 47 is a good exercise. And probably if you know how to do 47, you know how to do all of them in here, because it uses that new favorite formula for sum of geometric series. All right, I'm going to stop.